So this is lecture 2, and so what I'm going to do here is, in the previous lecture I talked about trying to simulate the universe including only the dark matter, and not all of the more complicated physics of trying to figure out what the baryons are going to do. And now I'm going to talk about adding in the baryons, and then also sort of exploring some potential alternative dark matter scenarios and seeing what that would do in terms of observables on small scales. So this is a dark matter only simulation representing what the dark matter very well might look like in the local group. So just to set a scale, this is about 6 megaparsecs across, and one of these big things is supposed to be the Milky Way and the other one's supposed to be M31. And then there's all these dark matter clumps everywhere around. Those are presumably the potential sites of dwarf galaxies. But of course, that's not what we see when we look at the local group. When we look out of the local group, we see something more like this, where we have the big Andromeda galaxy and Milky Way. There are a few satellite galaxies all around, but you certainly can't see all that rich dark matter structure. And so what we're trying to do then is we're trying to inform our knowledge of this dark matter distribution, trying to figure out if the dark matter actually looks like this by studying these structures and testing models that way. In order to do that, you have to include the normal matter. Yes?
The simulation is a constraint simulation. You're trying to, this simulation is trying, you put some data that to reproduce the local group?
Yeah, so the question is this simulation constrained in some way so that you reproduce the local group? And the answer is yes. So effectively, what we actually did in this simulation is we ran a lot of big simulations, or effectively a very big volume. And then we looked for pairs of dark matter halos that had similar mass to the Milky Way and M31, were approaching each other at the same speed, and had similar large-scale structure as the local group does, in order to pick out systems that looked like the local group in that way. And we did that in order to sort of do direct comparisons to what we then see around the local group specifically. We're actually doing this with full hydrodynamics now. I could even show you a movie later if you want of what that looks like. Now, in order to do this, the kind of simulations you have to run in order to capture the full baryon physics is actually harder than the dark matter physics. The dark matter, at least the standard collisionless cold dark matter, is pretty easy to deal with because it's just dust. So there's no real pressure. Everything's basically gravity. But when you start including gas, you have to solve hydrodynamic equations. I'm not going to go into detail at all about how you do this, but I just thought I would mention that there's different ways that people approach the hydrodynamics problem in case you sort of see this and run across it. It sounds somewhat familiar. There are different methods that you can choose to solve the hydrodynamic equations. One of the most popular ones is called smooth particle hydrodynamics. This is what's used, for example, in the code Gadget that is pretty popular. Also gasoline and some other codes like that based on gasoline. This is the idea that you basically have these particles, and the particles have a kernel that you smooth around, and then you solve the hydrodynamic equations based around these kind of smooth particles that sort of track and flow. The other possibility is to use a mesh or some kind of grid. That's either a fixed mesh, which is a fixed grid that doesn't move, or an adaptive mesh that sort of you make the grid smaller in areas where things are denser. So here's an example of an adaptive mesh code where they're trying to capture fluid instabilities between dense fluid and a less dense fluid. And you develop Kelvin-Helmholtz, and then you try to refine the grid where it gets denser here at the interface. Then there's another kind of, in principle though, there are problems with this, because whenever you have a grid code, well, there's problems with all these methods. Let me explain them first, and then I'll talk about other methods. There's the other ideas, which are meshes like this, but they're not fixed, but they move. So effectively, you kind of have particles, or the center of your grid, which is moving, and then you build a grid around it and solve equations across the boundaries. And then there's something that's become only recently kind of come into astrophysics, which are ideas of mesh-free codes that are kind of a hybrid between SPH and moving mesh, where you kind of fuzz out the boundaries in some way, where you kind of include both sides on the boundaries. And these are methods, I think, that were developed by people who were doing like more hardcore fluid dynamics to kind of solve both problems. So one of the problems, for example, with smooth hydrodynamics is it artificially smooths out instabilities. So if you had some dense structure of if you had sort of some fluid instability that you were creating, if you tried to resolve this with smooth particle hydrodynamics, you might smooth out the interfaces entirely because you have these big kernels, and that would sort of smooth out the interfaces, and you wouldn't capture the instabilities, and you might create false blobs that wouldn't really survive, like cold gas blobs embedded in hot gas surroundings that weren't real, that are just numerical. You can have the other problem with grid codes because by definition you have discontinuities at the boundaries of the grids. So then you can lose accuracy at the boundaries. And so these meshless formulations are trying to sort of do both at the same time. The point is, the hydrodynamics is harder than just following the dark matter physics, and these are things that people are worried about, and you're constantly trying to make sure you're getting the hydrodynamics right, and you're not just fooling yourself and you think you're learning something about physics, and really you just have some numerical issue. Then on top of that, you have to then model other things that are going on in the universe that you usually can't resolve directly in a cosmological simulation. So you've got star formation. So stars form. Stars are forming at incredibly small scales, much, much smaller than a resolution element in your simulation. So you have some kind of prescription to deal with that, and I'll talk about some examples. You have radiation pressure, so you have radiation coming off of these, especially low-mass stars, that can then sort of push on gas and drive gas out. You have direct stellar winds. Stars have these winds where they're losing mass as well. You have photoionization that can heat gas. You have supernovae that can impart energy and momentum in, for example, local SPH particles. And then active galactic nuclei. And so all of this stuff, excuse me, I'm going to trip over my own shoe. I don't want that to happen. So all of this stuff requires some kind of subgrid physics. That is, you're not modeling it directly in your simulation, you're including some kind of recipe to capture it. And exactly how subgrid it is depends on the resolution of your simulation. So really low-res simulations have to treat star formation in a very different way than very high-res simulations. And I'll talk a bit about that. But if you don't have the resolution to resolve an individual molecular cloud, then you're doing something very smooth over the, you're basically forming stars over an entire galaxy, which is not really how stars form. If you can get to the point where you can resolve an individual molecular cloud, that's a different kind of subgrid recipe than you would have if you weren't resolving that molecular cloud, for example. Are you doing, are you actually tracking photons as they come off of stars and then creating radiation pressure in the system or not? Or are you just mocking that up in some gross way? These kinds of things. The bottom line is, real galaxies do have supernova winds. They are emitting UV radiation, and so we want to at least capture these kind of effects in the best way, at least as best we can. So this is just an example of a paper I was involved in that with a specific set of feedback recipes called FIRE. And here in this paper, we were investigating all of these different kinds. This is Phil Hopkins stuff, investigating all kinds of different sort of scenarios and how much they affected galaxy formation. And you're not supposed to be able to read this. You're supposed to see just a bunch of stuff. So it's mass resolution, force softening, gas force softening, dark matter force softening, time stepping, whether you're using smooth particle hydrodynamics or some meshless kind of hydrodynamics, how you're dealing with pressure in the gas, all your different cooling tables, whether or not your cooling depends on metallicity, how you're doing metal mixing. There's a lot going on in a lot of these things. So just realize there's a lot under the hood in a lot of these simulations, and so you have to sort of, it's constantly, how robust are these predictions, et cetera, the kind of thing you have to think about. But it's actually remarkable how successful a lot of these simulations are at reproducing things that look kind of like real galaxies. There's two general class of cosmological simulations you'll see. Some are big and some are small. That's basically it. There's really big box simulations that are cosmologically representative. So imagine they're like 100 megaparsecs on a side. And in those, you're creating entire populations of galaxies that you can look at statistically, try to ask kind of global questions. So the good thing about them is they're representative. You have lots of galaxies in your simulation. The bad part is they tend to be lower resolution because they're running these big volumes. And so you're not resolving that well individual galaxies. The other approach is to do a zoom-in simulation. And this is basically throwing all your compute power, usually in just one galaxy or maybe just a few galaxies in a local region, and simulating those to incredibly high resolution. These will almost certainly always require different subgrid models because you'll be resolving different scales here than here. These will always have a smaller sample size, right, because you're doing zooms, but they will be higher resolution so you can attempt to try to resolve the individual the structures of individual galaxies. These are going to be most relevant for the problems that I've talked about today because the problems that I pointed out have to do with the structure of galaxies on very small scales. So this is how it's with these zoom-in runs that you can achieve force resolutions of order tens of parsecs in a cosmologically self-consistent simulation. Here are some examples of large cosmological volumes with full hydrodynamics that you may have heard of. So the Illustris simulation is one example. The Eagle simulation, and here's one here called Massive Black. These classes of simulations actually do a good job of matching many global parameters in galaxy formation. So things like the stellar mass function, the star formation history of the universe, etc. However, they do less of a good job of actually reproducing the detailed structure of individual galaxies, reproducing spiral structure, really thin disk galaxies. They tend not to really get the gas content of individual galaxies right. Stuff like that they get wrong. But again, this is probably where it's their resolution, et cetera, that's starting to hurt them. You will sometimes see pictures like this from, say, for the Illustris group, but this is like the best galaxy in the whole simulation. If you look at all their galaxies, most of them don't really look like galaxies. This is being recorded, isn't it? That's hi, Mark. Okay, so zoom-in simulations are another approach. And so here's an example of a zoom-in simulation by Guedes et al. This is called the Eris simulation. And this was one of the first simulations to achieve the reproduction of a galaxy that really looked a lot like the Milky Way. In fact, this is an edge-on view of the Eris simulation. They even modeled the dust. And this is an edge-on view of the real Milky Way. And boy, you're starting to create galaxies that actually look pretty good here. One of the crucial things that simulations like this are able to do is they're actually able to resolve overdensities in gas that are quite high. That is, their particle mass is small enough that they can begin to some regions of their galaxy might have overdensities of 10 or even hundreds in atoms per cubic centimeter, whereas other regions of their galaxies will have very low densities. Now we know that in real galaxies, you basically need really high overdensities of gas, molecular clouds, to form stars. You don't form stars out in the middle of nowhere with low density gas. And so what they're able to do is then in their model, they impose a star formation density threshold. That is, when gas gets above this critical density, it's allowed to form stars. When it's below that critical density, it just stays gas. And so with this kind of resolution, for example, if this is their star formation threshold, and this is a function of radius in their galaxy, there's pieces in the galaxy where the gas gets dense enough to form stars. But there's a large swath of the galaxy that doesn't form stars. In older simulations, and in fact these large volume simulations, they necessarily have to set this threshold lower because they can't possibly resolve densities higher than that because their particle mass is so big. And so what happens then is that if that was the case, your whole galaxy would form stars as opposed to just pieces of your galaxy would form stars. And that creates a very different structure. Yeah?
So, I mean, does that threshold coincide with the gene's mass? Or you have the temperature, you have the density, so...
Right. So you also impose that the thing has to be genes unstable as well. But just in addition to that. But usually once you reach these densities, you are. This tends to be the most important thing, but then on top of that...
So you said that, you could lower that threshold, and that threshold is still above...
At some point it's not. You're right, at some point it's not. But in the very low-res simulations, they don't impose that because they just can't resolve it. They can't resolve the gene scale. So in the highest resolution simulations, you can resolve the gene scale, and that's why you start to believe them more. You're actually physically resolving things. At least you hope. Yeah. Right. So does that make sense? This kind of general. So that's why going to high resolution is nice. You can start developing these kind of more realistic structures. So these images are actually from the fire simulations. And this is this is an edge-on view of a Milky Way-sized galaxy simulated with about 4,000 solar mass gas particles. Sorry. Yeah, 4,000 solar mass gas particles, I think, in this simulation. Yeah, so that's pretty good. And this is a face-on view, an edge-on view of a different galaxy. And you see, just by eye, you're creating spiral arms, you're getting dust lanes. And these galaxies actually sit on the M-star M-halo relation of the kind I was showing before. That is, they have the right stellar masses for the halos that they're inhabiting. So let me just show you a movie of how a galaxy I think it was actually this galaxy here, formed as a function of time. So what's going to be shown on the left is the gas. What's shown on the right will be stars. Now the gas is color-coded by temperature. Pink is cool, and red is going to be very hot. And green here in the middle is kind of like warm. So this is at a high redshift around Z of 13. And then over here you'll see the stars. And so the stars are on the right, the gas is on the left. The other thing to keep in mind is this bar is 10 kiloparsecs across. And this little bar is 10 kiloparsecs on the left. So the gas view is a little blown out compared to the star view. So that green was reionization turning on when it all went green. So there's a lot going on here. There's a lot to look at. But if you focus on the gas, for example, what you'll see is a spinning ball here. This is going to be the disk galaxy. But you'll also see a lot of kind of outflows and little explosions. Those are supernovae going off and parting energy and momentum into the gas and blowing gas out and heating it up. So there's this hot halo that's developing around the system, and then you have this spinning ball of gas that's sort of self-generating an ISM in the galaxy. So it's, you have this stable gas disk, and then on the right you have this stellar disk that's building up over time. And of the sort of 15-ish Milky Way-sized galaxies studied in this paper, this is the most disk-like. This is the most disky one that formed, so I'm showing that one because it's most dramatic. But it's a great big disk. Like this bar is 10 kiloparsecs across. It's a big spiraling disk. There's all this kind of gas structure coming in. And it's incredibly stable with time. Yeah?
So you said that the stellar mass halos were having the right size dark matter halos, but how are they seeded in these simulations? Like how are the baryons and gas seeded?
Oh, they're seeded according to what you would expect from cosmology. So basically you have your initial power spectrum of dark matter, you have your initial power spectrum of baryons, and you let it go. The only different thing in the initial condition is at redshift 8, we reionize the universe externally. So we let the gas reionize. So you could see that in this movie. Boom, that was reionization. So that was the other flag that was turned on. Something else? Yeah.
I have two questions. Is this reionization just put by hand?
Yes. So in these simulations, the reionization was put by hand. There are a lot of simulations that attempt to actually capture it from first principles. We put in a reionization history by hand that matches like Planck constraints on the reionization history globally.
The question is with respect to the, we live in a galaxy with a very thin disk.
Yes.
And I was told many times that actually it's not clear how could it be, it would have to be a very quiescent past in order to have such a thin disk.
Yes.
Is this galaxy one in which in particular you didn't have many blobs, it has particular, in order to get this thin disk, what happened to this galaxy?
So what we find is that it's very important that you not form too many stars early to maintain a thin disk. So this galaxy actually has a lot of cold gas late, and cold gas cools and kind of recreates thin disks. So like you can heat it up, then it recools. And so as long as you don't form too many of your stars very early and puff up the stars, you can potentially form a thin enough cold stellar disk. But I would say that in this class of simulations, the hardest thing that we have in reproducing is sort of the thinness of the stellar disk of the Milky Way does remain, I think, a little bit too thin compared to these results. But it's not like crazy thick. It's not crazy thick like in the old days. I mean, you can sort of see here, you know, this is stars. So these disks are pretty thin in stars. And so we're able to create pretty thin disks at least sometimes, you know. I actually have, it's maybe we're showing it just to show another example. This is a local group. Whoops. Hold on. So this is a local group region, and I like it because this one's shown. I'll start again. This is 100 kiloparsecs across. This is redshift 13.6. This is all the gas that's going to end up in the local group starts off in this region. So you can get a sense of what we're doing with these zoom-in volumes. And then the thing's going to be expanding with the universe as it gets bigger, and then you'll see it recollapse. So that was reionization turning on. And now you'll see, look at the little dwarf galaxies start forming and blowing hot gas out as they're forming stars. They're generating these kind of hot gas envelopes around. But here you can really see, if you focus on it, supernova going off and kind of blowing gas around. And that's going to be very important in the stuff I talk about later. So here's a spin up of what's going to be a Milky Way, and here's a spin up of what's going to be an M31. So the whole thing is expanding apart. Gravity begins to sort of slow it down, and then eventually it past Z0. They will approach each other at a pretty high speed. But there's just little gas blobs and stuff everywhere here creating this stuff.
James, you're hinting that, you know, supernovae are fine up to a point.
Yeah. So then the real question is, you know, when does supernova stop doing their job? So this is actually a zoom-in. This is a zoom-in simulation of a different galaxy. This is a dwarf galaxy. So this is a dwarf galaxy, kind of closer to the classical dwarfs. And this has like 500 solar mass gas particles. So this is really very high-res simulation. And what's plotted in black is if you run the same simulation with dark matter only, and red is if you run the simulation with full hydrodynamics, what you get for the dark matter density structure. Okay? And so what you see is going on is this red line is lower than the black line, and in fact it's bopping around. And what's happening is as supernova explode, it's shocking the potential, and the dark matter is reacting to that and no longer filling that loss cone, and it's creating this kind of a core-like density profile. This thing ends up forming a few million times the mass of the sun in stars. And it does create a pretty sizable constant density core in a pure dark matter simulation, a collisionless cold dark matter simulation.
Can you reproduce the bar, like the galaxy with the bar?
The galaxy with the bar, not in this system, because this system is a tiny dwarf, and dwarf galaxies don't have bars. Do we ever see bars in our galaxies?
In previous simulations, you just see like.
Yeah, that's a good question. I do not know. So we have. That's a good question. I think we do occasionally see bar-like structures in those central galaxies. But we only have of order 10 simulations done at this resolution for a Milky Way-sized system. And I think one of them does have a bar-like structure. But this certainly, you know, does not have a bar. This one doesn't. Yeah. Yes?
In this simulation, I created a core. How many supernova events in total?
How many what?
Supernova events happen in the dwarf galaxy.
You typically have about one supernovae per 100 solar masses of stars that form. So this guy formed a few million, so a few tens of thousands of supernovae. And you're getting to a good point, which I'll turn to right now. As you form a lot, if you form a lot of stars, you have a lot of supernova that can go off, and therefore a lot of energy at your disposal to push the dark matter around. This one formed 10 to the 7 solar masses of stars and created a nice core. This one formed a few million solar masses of stars and formed kind of a core Not as cuspy as dark matter only here in dash, but not much. This one formed only 5 × 10⁵ solar masses of stars and looks exactly like the dark matter only simulation. This thing would have only had a few thousand supernovae go off, which is not that much energy. And you would have to couple that supernova energy really directly to the dark matter really to do anything. And of course, it's not coupled directly to the dark matter. It's only coupled to the gas. And then, so what we're getting at here is that below a certain stellar mass galaxy, supernova can't do that much. And so there's a sort of a prediction here. And I should say, this is all done with fire feedback. And the fire feedback scheme is a pretty aggressive feedback scheme. So like many other feedback schemes in the literature are not quite as aggressive with their feedback. So this is a fairly aggressive feedback scheme. And it's not able to produce much core-like behavior in the dark matter profiles of low mass dwarf galaxies. So in fact, what's plotted here is sort of a combination looking at actually 2 different simulation suites done by 2 different groups that I've called frenemies. So, you get, 2 simulation groups together, they're constantly like nitpicking each other and my simulation is better than your simulation, And so they're kind of on the same team, but they really don't believe each other. But anyway, so this is the Nihao group. And this is the fire group. And what's plotted here is the log slope of the density profile at about the radius where the stars live, at about the half-light radius, okay? And so the point is, the closer to 0 this slope is, the more like a core it is. So up here is core-like, down here is cusp-like. And NFW lives right in this band right here, okay? And so both simulation groups broadly see the same thing in that there's a characteristic scale in m star over m halo of a few times 10 to the minus 3 where you get maximal core formation. So this is kind of where you might be forming about 10 to the 8 solar masses of stars in maybe a 10 to the 11 solar mass halo, something like that. This is like an LMC, sort of SMC kind of system. You create giant cores, because in this case you've got a fairly shallow dark matter potential well and you've formed a fair amount of stars, and those 2 things together allow you to produce a pretty big core. But as you go to really low mass galaxies, that is, you don't form that many stars, you don't have that many supernovae, you return to this cusp because you just don't have enough energy to push dark matter around and it looks like a dark matter only simulation again. And so just the fact that these 2 very different groups, this uses SPH with different feedback scheme. This is a meshless finite mass, sort of a meshless hydro scheme with different sort of feedback implementations. They're both broadly seeing the same thing, and that's because this broadly has to do with energy conservation. I mean, at some point, you just don't have enough energy in supernovae to alter the cusp. Another thing that's kind of interesting actually is you actually see steeper than NFW for really big galaxies. What you're seeing here is something called adiabatic contraction or baryonic contraction, where you grow a galaxy in the center of a dark matter halo and that brings dark matter in and makes it even cuspier in the dark matter only simulations. You're getting log slopes of -2 in the center of these galaxies. And this is exactly what you see in lensing, by the way, that the most massive galaxies tend to have density profiles that are quite steep. And this is in fact what you see in a lot of these simulations. -2 log density profiles at small r. And this is a baryonic effect. So anyway, this is what you see. But the fact that these 2 different groups are seeing qualitatively the same thing, even though there's lots going on under the hood, I said, this suggests that there's some kind of robust result here. Yeah?
Is this lowering branch to the one due to baryonic effects, and the other is just the
So this is kind of like contraction.
contraction?
Yeah. So there's so many baryons that it actually overcomes the supernovae effect.
And the other is?
This is supernovae. Yeah. So it's like supernovae gradually become more important as you add stars, and then contraction becomes important at some point, and they meet in the middle at this kind of middle scale. So contraction makes you steeper, supernova make you more core-like, and then they kind of like overlap at this kind of middle scale here. This is the mass scale of LSB galaxies, right, that actually have big cores. So it's kind of what you see in the real universe, although there needs to be a much more precise comparison here. Yeah?
These are all, I assume, done with the conventional IMF and
This is all basically conventional IMF and stuff, yeah.
another knob one could turn if you had really low metallicity environments. And I don't know what initial metallicity.
Yeah, well, the metallicities, and especially, I know our simulation's better, it's like 10 to the minus 4. So you could play with some crazy IMFs and get some more energy there. You know, more high mass stars. And those things obviously wouldn't live. So you may have a lot of high mass stars that don't live long, but then you push the dark matter around a lot then. So maybe, yeah. So, one kind of broad, I mean, this isn't written in stone, but this is qualitatively kind of where people are now. Below stellar masses of about 1 million, there might not be enough energy from supernovae to alter dark matter structure. This is interesting because this is the mass scale of too big to fail. And it's also a mass scale where you do see some core-like rotation curves, although it's sort of at the line. The real holy grail would be to somehow measure the density profile slope in an ultra-faint galaxy. Maybe if you had proper motions for individual stars, you could do this. If you saw a smoking gun core in the center of a 10 to the 5 or even lower mass dwarf galaxy, that would be bad news, I think, for this class of dark matter models. So what would you do then? Well, you might appeal to something like self-interacting dark matter. So the idea of self-interacting dark matter was proposed by Spergel and Steinhardt in 2000. And one of the primary reasons why they proposed this model actually was to solve the missing satellites problem. It turns out it does not solve the missing satellites problem and doesn't affect substructure at all. But it's still a very interesting model. And the other thing they pointed out in this paper is that it could also produce dark constant density cores in dark matter halos, and that it does. So the basic idea is you have a cross-section for self-scattering. And again, this is dark matter scattering off of dark matter. It's not dark matter scattering off of baryonic matter or nucleons. And it's typically normally, you know, a scattering rate would be number density times cross-section times velocity. But we don't know the number density of dark matter particles because we don't know the dark matter particle mass. So instead you write the mass density and you write the cross-section as the cross-section per unit mass. And so that's the relevant number. And it turns out that if the cross-section per unit mass is of order 1 centimeter squared per gram, which is like a barn per GeV, then the rate is interesting in a Hubble time. That is, in a Hubble time, you're going to get a couple scatterings. And so that sort of sets the scale of interest. Now, I should point out that most models would have a cross-section that depends on the velocity itself, like any kind of nucleon cross-section would. But for the models that I'm going to talk about, just to simplify things, we're just going to be running constant cross-section models. The idea being that if you're running a simulation of a dwarf galaxy at a velocity dispersion of 10 kilometers per second, you are constraining the cross-section at about 10 kilometers per second. If you're running a simulation of the Bullock cluster at 1,000 kilometers per second, then you are constraining the cross-section at a velocity of about 1,000 kilometers per second. Other folks actually just build in a velocity-dependent cross-section and run models that way. There's a whole group called Ethos who do things that way, which is a very interesting and I think very, very useful approach. But I'm not going to talk about it, just to sort of to keep things simple. Yes?
What is the Hubble time?
Sorry, the Hubble time is like the age of the universe, like 14 billion years. Sorry, yeah. So it's just like in the age of the universe, do you scatter once or twice? Yeah.
So what kind of velocity dependence?
No velocity dependence at all. We just assume a constant cross-section. But I'm saying that what I will show you is results for a system that has a characteristic velocity dispersion. And so in your head, you could say, okay, well, that's the constraint for a cross-section at that velocity dispersion. See what I mean? So we're not actually imposing that at all so far. Some groups have, but I'm not going to show you any results from that. Actually, I'll show you one slide from that. Sorry, there is one. Yeah. Okay. So what does SIDM do? So here's a Milky Way halo run with CDM. Here's the exact same halo run with SIDM. So if you look at this picture and you look at this picture, you can see why SIDM does not solve the missing satellites problem. This is run with 1 centimeter square per gram cross-section, and even substructure by substructure, they're in exactly the same place. You can tell the difference if you really focus on the middle, the very middle of the system. This thing is a little rounder and lower density in the center than the CDM. You can see it here if you plot the density profile. So what's plotted here is the dark matter density profile of this halo and cold dark matter, and then the same halo and self-interacting dark matter. And you see the self-interacting dark matter halo creates a gigantic constant density core. Now, the reason why SIDM creates these constant density cores is because there's a heat flux. So what's shown here is density profiles for different run for the same halo but with different cross sections. So high cross sections make bigger cores, the black line CDM. But on the right is the velocity dispersion profile of the dark matter as a function of radius. And so the black line shows the velocity dispersion profile of cold dark matter. And what you see is the cold dark matter halo is cold in the middle and hot in the outer parts. And that's very characteristic of cold dark matter. That's why it has a cusp, because it's cold in the middle and hotter in the outer parts. When you have a self-interaction, what happens is particles can scatter off of each other. So what happens is a fast-moving particle can scatter off a slow-moving particle, and the system becomes isothermal. And so what's happened here is that as you increase the cross-section, the radius where you get scattering is a little bit larger, and you get a little isothermal profile right here in cyan. For a very high cross-section, you get isothermal all the way out through the whole system that's plotted. So as the particles interact, they distribute energy, and the whole thing becomes isothermal. When the system's isothermal, that's what creates the core. So you have an isothermal core. So that's the process that creates cores in SIDM halos. You're not actually knocking dark matter particles out of the core so much as you're just becoming isothermal. And it's the isothermality that creates that core. And that's all SIDM does. It just makes halos isothermal in their middles. It also makes them round in their middles. They have isotropic velocity dispersion tensors too, at least if you have an isotropic scattering. So as you increase the cross-section, you make bigger and bigger cores. There's some other phenomenology that's kind of fun with self-interacting dark matter, and that is you can get core collapse. So what happens with core collapse is if the system becomes a little hotter in the middle than in the outer part, and this is kind of rare, but you can have a system where the dark matter is hotter in the middle than it is in the outer part, then you can actually start transferring heat not from the outside in, but from the inside out. And so if you transfer heat from the inside out, you come cooler in the inside. As you become cooler, your pressure support drops and the whole thing shrinks. When the whole thing shrinks, it actually gets hotter again. Then you transfer heat out and it shrinks again. And so this is the kind of process that leads to core collapse globular clusters. But you can also create core collapse dark matter halos this way. And it's possible that this occasionally happens and can do things like create black holes. Like it's possible that there's some formulations of self-interacting dark matter that can actually generate early black holes and things like that. That's a phenomenon we see in our simulations, although it's fairly rare. Yeah?
So looking at the plot on the left, it
Yes.
looks like the core size increases monotonically as you increase the cross-section, right? But then the last three, it has this
funny thing, so that you're seeing core collapse.
Oh, that's core. Okay.
Right, so what happens is it gets more core-like down to a cross-section of about 5. And then as once you get the cross-section of 10, it basically stabilizes. And if you go to a cross-section of 50, it actually gets denser. And so you're seeing core collapse. And another thing we've seen, although I don't show it here, that if you start growing galaxies in the middle of these halos, that accentuates core collapse. And so if you have like a CD galaxy, like a big elliptical, we think that basically you can get crazy amounts of dark matter in some models that it just core collapses in the center of an elliptical galaxy. And so I think that it could be interesting constraints on certain models actually trying to constrain how much dark matter there is in the center of elliptical galaxies. But cross-tensors of order a few are sort of like are reasonably robust to core collapse, except for in extreme cases of very baryon-dominated systems, then you might see it. But that's a way you might actually produce big black holes. This is what I mentioned. This was the model I was referring to. So Volkersberger et al. Have run a series of models where they've actually looked at cross-sections that vary with velocity. And so these are just different models that they've studied where you actually have self-interacting dark matter models that have velocity-dependent cross-sections. But you qualitatively get the same thing, that, you know, if the thing has a high cross-section at the velocity dispersion of the Milky Way, about 100 kilometers per second, then you get big cores and Milky Ways. Okay. So SIDM can solve the too big to fail problem. So basically you increase the cross-section, that makes you have a core that's pretty large, that lowers the central density, and takes your dark matter halos that otherwise are too dense in CDM, and they become less dense, and they match the data. Other questions about this? So warm dark matter, what is it? Just as another alternative, rather than SIDM, which, by the way, I should have clarified this, but generically, if you just have self-interacting dark matter, you can have a cold self-interacting dark matter. So what that means is you have a power spectrum that looks like this. The only thing that's different is you have this collisional interaction among the dark matter particles. So when I talk about self-interacting dark matter, I'm talking about cold collisional dark matter. Okay. Another possibility is the dark matter is still collisionless, but it's warm. That is, something happens because of its thermal mass, or if it's a stereoneutrino, you could chop off the power spectrum basically because of free streaming, right? So what happens then? Well, so here's the same experiment, the same halo run in CDM, but now with warm dark matter. This warm dark matter model has a thermal mass of about 2 keV, which is marginally ruled out, but just to show you an example. And what happens here is there's less substructure. So what's plotted here is the number of subhalos, now plotted as a function of Vmax, but you can think of it as mass. CDM is this black line, and warm dark matter is this dotted gray line. So you see really suppress substructure in these models because you're wiping out power on small scales. So you see that it's different than SIDM, and in fact, and I'll return to that comparison again, because if you remember, SIDM doesn't change the substructure at all, but changes the density profile. Warm dark matter doesn't change the density profile at all, but changes the substructure. They sort of have different effects. Of course, the amount of substructure you see depends on how cold the dark matter is or how warm the dark matter is. As you approach lukewarm dark matter models, they look more like CDM, and if you make the dark matter warmer and warmer or hotter and hotter, you reduce substructure more. And so you can get to the point where you're counting galaxies and trying to use that to constrain your models. So this just sort of summarizes everything I've said about these two classes of dark matter alternatives. Okay? This is cold dark matter. This is your cold dark matter Milky Way. This is your self-interacting dark matter Milky Way. And this is your warm dark matter Milky Way. So self-interacting dark matter has the same substructure mass function as warm dark matter, but it has a big core in the dark matter density profile. Warm dark matter has much less substructure than cold dark matter, but it has the same dark matter density profile, at least for a Milky Way size system. So they do two very different things. Okay. Yeah?
Could we look at the figure that shows the linear metal spectrum for the warm dark matter? Yes. So the cutoff happens at somewhere 10 to 100 meters per atomic scale, and it falls very smoothly. And this is because that warm dark matter is freely streaming. But what if the warm dark matter, the dark matter has some kind of interaction, so it falls off like kind of oscillating? Mm-hmm. Yeah. So in that sense, they have the same cutoff scale, but like they fall kind of differently. Yeah. So does it affect all this modeling?
Yeah, so that's a really interesting question. So we've looked, yeah, sorry. So the question is, imagine this fall off in the power spectrum comes from a specific model of thermal warm dark matter, so it has a very kind of smooth rollover. But imagine you had a model where there was some kind of coupling in the dark matter, so it created some kind of wiggles. It had structure on the way down. Does that manifest itself in any way in sort of the low redshift predictions? So I can't answer that specific question, but in this, a series of papers we wrote with Horiuchi and then Brandon Bozek that came out in 2016, we were actually looking at a related question, which is the difference in what you get if you actually use a realistic power spectrum calculated for a stereoneutrino dark matter case, the kind George has worked on, and what you get in just a thermal warm dark matter, right? So they have sort of slightly, they fall off in a different way. And we were trying to see if there's any sort of nonlinear differences in those models, so that would be really cool. What we found is that in substructure at low redshift, very, very nonlinear stuff, it didn't matter that much. It was sort of like the half mode was all that mattered, and you couldn't see very big differences. But a place where you started to maybe see differences is in high redshift galaxy counts. So at the point where sort of mildly nonlinear, when things were going mildly nonlinear, you might start seeing things right at that scale. And so this might be redshift 10 galaxy counts, for example. And I can imagine if you had a more extreme difference, where you really had some wiggles, maybe you could start to see something. That would be kind of a fun thing to explore. But my guess is you would see it at high redshift in the mildly nonlinear regime, as opposed to the very nonlinear regime of substructure, once it's already kind of been mixed up in subhalos and stuff. Yeah, that's a great question. Okay. So, summary, warm dark matter, less substructure, similar density profiles. SIDM, similar substructure, core density profiles. Okay, so now I'm going to try to put the baryon physics. So what I've done so far is I talked about baryon physics and what it can do. And then I said, okay, well now let's talk about changing the dark matter physics. Now let's change dark matter physics and do the baryon physics at the same time and see what happens. Yeah?
Can you test now or in the future this, do you have enough data, good quality data to test this?
This?
What's the style, right? Similar?
So yeah, I mean, I'm going to sort of get to that a little bit. I think, for example, in the nonlinear regime, I haven't talked about the Lyman alpha forest at all, but so the Lyman alpha forest is a way you can sort of directly try to constrain the mass, the power spectrum in warm dark matter. That is sensitive to knowing what the IgM temperature history was, which is a little bit uncertain. And so that places some ambiguity on your constraints. So an alternative way, two alternative ways of testing warm dark matter in this way is just going out and counting galaxies. Okay, so like if you counted the number of subhalos here total, there's probably only 100. It's very plausible that after the error, we already know of 50 galaxies. And it's very plausible that in the error of LSST, we'll know 300. Right? And if that was the case, this is done. So just by counting galaxies in LSST within the local volume, you could imagine ruling out warm dark matter models, which would be pretty cool. So that's one way. Another way to do it is actually by counting galaxies at high redshift, because warm dark matter, because it has less power, if you remember this, this sort of cartoon I had that, the linear power spectrum, you just back it down to high redshift, because there's less growth. Well, if this thing, at high redshift, there's nothing that's collapsing in this model at all, right? So at high redshift, it's only these mass scales that are collapsing, right? But there's no power on those scales at all in warm dark matter. So you don't have any galaxies at all living at, say, Z of 10. Just nothing. There's nothing that's collapsed. I'm just saying an extreme model, right? So you can imagine in a JWST ultra deep field, you're counting galaxies at redshift 12 and you have some number density. There might not be any collapse structure at all at Z of 12 in certain warm dark matter models, in which case you could argue that those are ruled out. So in the era of JWST and LSST, you might actually be ruling out models by just flat out counting collapsed objects, which would be kind of interesting. For SIDM, let me talk about that now. So here's an example, a series of dwarf galaxies that we've run with full fire physics at very high force and mass resolution in both self-interacting dark matter and cold dark matter. What's plotted here is the stellar mass growth histories of 4 different galaxies. And they're color-coded by the stellar mass they end up with at z equals 0. So the yellow one forms 10 to the 7 solar masses of stars, and the blue one forms a few times 10 to the, well, about 1 million solar masses of stars. So the thing you're supposed to take away from this is they're not that different. They're within the noise of what you get in a galaxy formation simulation. These are pretty darn similar star formation histories. The only exception is this one. But still, it's not that different. So broadly speaking, star formation histories look pretty similar. It turns out their sizes, their stellar masses, their metallicities, all of those things are actually very similar in SIDM and CDM. The only place we see a difference is in their density profiles. So specifically, if we go to one of the smaller galaxies, this one here, right? This one forms so few stars in cold dark matter that it creates a nice cusp. There's not enough supernova to make a core, whereas in SIDM it preserves that big core. And we see this fairly robustly, and so the point is that we think this is a fairly nice falsifiable prediction for this class of self-interacting dark matter models, that if you see cusps in low mass galaxies, that is going to be hard to handle in SIDM models. Conversely, if you see big cores in low mass galaxies, that's not good for CDM models. And so this is kind of an interesting kind of future direction to look to try to constrain, I think, self-interacting dark matter. Warm dark matter, it's actually kind of like before, it's sort of the reverse. The density profile structure is actually not that much different with full hydrodynamics and warm dark matter and cold dark matter. But what is different is the star formation histories. So these galaxies, so what's shown here is the mass growth in CDM, and this is the mass growth in warm dark matter. And in warm dark matter, these galaxies just form later. You know, these halos, you know, these same halos, same initial conditions, basically same random seeds, they basically existed at redshift 10. Whereas these warm dark matter dwarf galaxies did not exist at redshift 10. They just hadn't grown there yet. So, you know, there's 2 ways you would see this observationally. One is if you just have really deep observations of low mass galaxies, which will be possible with James Webb, you just don't expect to see that many faint galaxies, period. You expect the luminosity function to turn over. So that's one thing. And the second thing is, as you actually measure the resolved star formation histories of local galaxies, you expect to see more late-time star formation and less early-time star formation. And so the fact that we have all of these really ancient ultra-faint dwarf galaxies around us today, you could argue might be a bit of tension for warm dark matter, at least this sort of mass scale of warm dark matter model.
Remind me, please, all these blue galaxies that are seen in gravitational lensing, blue, very far away blue galaxies that are seen through gravitational lensing.
Yes.
How far are they?
Through gravitational lensing? Oh, are you talking about like the frontier fields, or are we talking about like the arcs?
Where you can see arcs, little arcs.
Oh, like the arcs?
Blue galaxies.
Okay, one of the, someone help me with some lensers tell me where the,
I don't know where.
I mean, they're like redshift 3. I think most of them are like ZF3-ish in a lot of these lenses. Maybe ZF1. It depends on where your lens is. Does anyone, do you know? Where are the arcs coming from, you remember?
Galaxy lenses are like, yeah, 2 or 3, but the big cluster lenses, I don't know how far away their galaxies AC are.
Yeah. So I mean,
nowhere close to.
Well, no, in the frontier field, no, we're seeing. I mean, in the frontier fields, you're seeing dwarf galaxies at ZF10. Just not that many. I mean, the numbers are very, very small. But in the today, with frontier fields with HST, you're beginning to measure luminosity functions of low mass galaxies at redshift 10. It's starting to happen now. So, and JWST,
So these big, now new super giant telescopes, this generation, this new generation.
yeah, I mean specifically the James Webb Space Telescope. If which will happen, equivalent of the Hubble Ultra Deep Field, that's going to happen with James Webb. And when that happens, that will be a really nice test right there. Yep. Yep. So that'll be fun to see.
I see, so you can't make this difference, just with discounting, you will be able to tell the difference.
Yeah.
So this is
Yeah, it's
something
crazy.
you
Yeah, it's nice. It's very robust. Yeah, just by counting.
Unbelievable.
Yeah, it's cool. Yeah.
This is neat.
Yeah, it's cool. And it's actually crazy robust because it's like there's literally nothing that's formed.
So I see, so it's not really the very difficult to measure
Exactly.
low stars, it's all very low.
Yeah, you're just counting stuff. Yeah, you're just.
But this is very far away. And
Yeah. I mean, the point is, right, that like, if you need, imagine you go to high redshift, so you take all the lines down by a factor of 5. And so only this line is above 1. You have to be above 1 to collapse. So here, there's nothing above, if you take this down by a factor of 5, nothing is above 1. So there's nothing is collapsed at any mass scale yet. So then there's nothing there. So you don't even have to do any astrophysics, really. You just kind of count collapsed objects. So in principle, that's, it's pretty robust. So, we did all the astrophysics here because it's cool, but like you didn't really have to do that. You sort of knew what you were going to get. Okay, when are we finishing? 3? Yeah.
I think it's redshift 9.
Redshift 9 frontier fields?
Yeah, I think.
From Bowens? Is this Bowens or Livermore?
I think that this is JWST future.
Oh, okay. Oh, yeah. Well, that's nobody knows. Okay, redshift 9.
you have all the time you need because we are going to 3:25.
Okay, good. We got a little time.
Or even more if you
So I want to talk about.
don't cat.
Okay.
It's,
Okay.
if we go ahead, it doesn't matter.
So now I'm going to preach because I think this is the most important thing. So I would argue that the most important thing we could be doing right now in nonlinear structure formation, broadly defined, is looking for these damn dark subhalos that are supposed to be out there we haven't found. Okay, so what's plotted here is, this is an oldish simulation. This was the Via Lactea simulation, and these are the Aquarius simulations. And let me focus on Aquarius for a second. What's plotted here is they took a Milky Way size halo, and they ran it with some mass resolution. That's shown in cyan. And then they ran it again. They increased their mass resolution by a factor of 8, and then another factor of 8, and then another factor of 8, and another factor of 8. And so they spent several million CPU hours at the time, which was crazy amounts because it wasn't as distributed, to extrapolate a power law. The point is, this is a crazy robust prediction. That as you increase the resolution, you expect the number of subhalos to just keep climbing. And there's no reason why it should stop in CDM until you get to the free streaming mass of CDM, right, which is an Earth mass or something if you have a WIMP model or something, right? So this just go on forever. So this is a huge missing satellite problem, right? You're going to have millions and millions of subhalos down to some mass. Not all of those have galaxies in them, right? Clearly, once you get down to a mass below, 10 to the 4 solar mass dark matter halo, there's no galaxy in that. That just doesn't make any sense. There should be lots and lots of dark, something like 10,000 subhalos with halo masses bigger than 1 million. And so we should find these things. Most of them should be dark, and if you could find them, it would be a big deal. There's a robust group of folks here at UCLA who are looking for this substructure via gravitational lensing. This is Tommaso Trejo's group. And there's lots of different methods using gravitational lensing to look for substructure with flux ratio anomalies. There's something called gravitational imaging. There's new ideas of using ALMA to find this substructure. And Euclid and SKA are going to find way more of these things. There's going to be so many gravitational lenses. We expect the samples of gravitational lenses to grow. This is going to be really exciting in the near future. Another possible way to look for these things is with stream heating or stream interactions. The idea here is that you have a thin stellar stream, like for example PAL5, and then little subhalos go through it and punch holes in it or mess up the orbits of stars, and you look for structure in these stellar streams. And so these are two ways that people are going to be looking hard for substructure. What I want to do is just make a bit of a cautionary tale that we, in order to sort of, for all of these efforts to reach their full scientific potential, we need to make sure we're giving these folks the kind of predictions that are accurate enough. And my concern is that the predictions we've supplied so far have been wrong. And the reason why I think they're wrong is that they're pretty much all based, up until fairly recently, on simulations that don't include baryons. So this is another fire paper. This is one of the halos I've actually been showing you before that's been named the latte halo. But what's shown here is the gas out to about 600 kiloparsecs around this galaxy. And this thing looks a lot like the Milky Way. But here it's shown in gas. This is what it looks like in stars. So this is a pretty cool picture in stars because what's shown here, it's down to really, really low densities. But you see all these streams of stars, right? We think that the stellar halo of the Milky Way is in fact filled with streams of stars. These are leftover from little dwarf galaxies that came in and got torn apart by the host potential and created the kinds of streams that we hope to use to look for this substructure, right? So we were actually seeing these streams around the real Milky Way. That's the residue of hierarchical structure formation seen visible in the stars around the Milky Way. Okay, so that's there. But I don't want to talk about the gas, and I don't want to talk about the stars. I want to talk about the dark matter. So what's shown here on the same scale is the dark matter of the same galaxy. This was actually the first fully self-consistent cosmological simulation with full hydrodynamics to actually be able to resolve these million solar mass subhalos. And you can see there's lots of subhalos. There's thousands and thousands of them. But what I want to do now is zoom in on the central region, because the central region is really where, at least especially for stream heating and potentially for gravitational lensing, that's most important for looking for all of these subhalos. And there it is. So this is the central region within 100 kiloparsecs shown around there, around the central galaxy that lives in there. And then now what I'm going to do is I'm going to show you this exact same halo that we ran without hydrodynamics. Okay, so this one took 1 million CPU hours, and the one I'm going to show you now took about 10,000 CPU hours. You will notice that they do not look the same. This is the kind of simulation that up until very, very, very recently has been the fiducial predictions for all substructure searches, right? But it's clearly not the same. Now, you might say, okay, well, clearly there's less substructure here, there's more substructure there. This thing is rounder, this thing is less round. But you might say, well, yeah, but you just said there's so much going on under the hood. You people are making things up with all of your subgrid nonsense. Who cares about this? Let's stick with this. I don't believe this. But would you believe that there is a galaxy in the middle of the Milky Way, right? You would believe that, right? So what we did is we ran this simulation again using just the dark matter, and all we did is we just stuck a galaxy potential in the middle that looked like the galaxy that formed here and did nothing else. So we just put a galaxy in the middle and ran it again. And this is what we found. So this is the full hydrodynamics million CPU hour run. This is the 10,000 CPU hour pure in-body run that was sort of the classical way to make these predictions in the past. And then this is if we just reran this one and just put a galaxy potential in the middle. And you see, this one looks a lot like this one. So what has happened is this thing has added gravity to the middle. And that alone has enough to destroy substructure as it passes close by. And it destroys virtually everything within 20 kiloparsecs of the central galaxy, just from dynamical interactions. So it has nothing to do with feedback. It has nothing to do with like subgrid, anything. It's just like put a galaxy in the middle of your halo. It destroys all kinds of crap. Tidal, basically tidal, yeah. Yeah.
So were those projected pictures?
These are projected pictures. And this is why I was telling you I was worried. I mean, you know, there's some stuff there. There is some stuff. So to make this a little, now here's, we actually ran 2 simulations of this resolution. The dashed line is what you get cumulatively as the number of small subhalos is a function of radius for the dark matter only runs, and the solid lines are the full hydrodynamic runs. So if you focus on this one, for example, within 20 kiloparsec, there's like 20 subhalos in this run. Within this full fire physics run, there's nothing. So all 20 of those little, and these are million solar mass subhalos, all 20 of those million solar mass subhalos are destroyed by just the presence of the disk. But then once you get out the virial radius, it's within a factor of 2. It's very similar. Now you might say to yourself, how in the hell is this possible? Because you put in like a 5 times 10 to the 10 solar mass galaxy and a 10 to the 12 solar mass halo. How is this creating all of this? And that's exactly what I thought. Like, I thought there is no way this can't possibly be physical. You know, and that's why we ran it with potential and found it. But basically what's going on is this. If you look at the dark matter only runs, okay, and look at all the subhalos as a function of radius, and now, so basically, what we did is we grabbed everything within 100 kiloparsecs at z equals 0. Okay, so you take this halo, everything within 100 kiloparsecs at z equals 0, and then track their orbits back and figure out what their pericenter is. So how close did they get before? And this is what the pericenter distribution is of all subhalos within 100 kiloparsecs. And so some of them are at pericenter now. So those are things that just happen to be at this point and spend most of their time outside. But most of them actually have pericenters within 20 kiloparsecs. So then you do the same thing in the full hydro runs and ask, what's the pericenter distribution of everything within 100 kiloparsecs? And you see everything that has pericenters within 20 is just gone. So basically, subhalos are on very radial orbits. And if you get too close to the center and there's a galaxy there, you get destroyed. And that is enough to create this huge effect, all the way out to fairly large radii in these systems. And it's a pretty robust dynamical effect. And I don't think it's that sensitive to feedback and stuff like that. So what this means is it doesn't mean that it's futile to look for this substructure, because especially for gravitational lensing, it depends on projection. So you're going to see things in projection along the line of sight, and the farther you go from the lens, the less disruption you're going to see. And so that's a big deal. I think for stream heating, it's not as good. I think, unfortunately, the 2 streams that we know about that are great for stream heating studies are both within about 20 kiloparsecs. And I think for them, this is not good. It depends on the history and all the stuff that happens before, but broadly speaking, I think this expected disruption is going to be very important for these predictions. And of course, then we're going to have to do it for warm dark matter models, and then you're going to get reduced substructure even more. The other thing I should mention is that this is going to make counting subhalos even more powerful constraint on warm dark matter, because warm dark matter will also be affected by the same thing. So all the warm dark matter subhalo counts I was showing you didn't include this enhanced disruption. If you included this enhanced disruption in warm dark matter, it's going to make many warm dark matter models even harder to reproduce, say, the satellite counts around the Milky Way and M31. So again, this is just another way in which baryons matter, and we got to figure out how to incorporate them as we try to test dark matter models. Okay, I think I will end there. Thanks.
Maybe I can add, because I have So in our galaxy, the baryons are the dominant, dominate the gravity, the gravitational. So gravitationally dominant are the gravitationally dominant component within a radius that is less than 8 kiloparsecs or something. So you are modeling something that is 100 kiloparsecs, and you see that actually this effect is huge in destroying. So how can it be that something so subdominant has this?
So the question is, right? So the question is, how is it possible that if you have something that's baryonically dominated, where the baryons dominate the gravity only within 10 kiloparsecs, how is it possible that it's affecting subhalo structure at 100 kiloparsecs? How is that possible? Well, that's kind of what I was trying to get to here, that a lot of the stuff that is right now at 100 kiloparsecs used to be within 20 kiloparsecs, because subhalos are on very radial orbits on average. So what this does is it preferentially kills the radial orbits, and it leaves you with more circular orbits. So the only things that survive are the things that don't come in close. So that's the main thing. Yeah, it's surprising, but I mean, we see effects even farther out. Like, it's amazing. It's amazing. And this is why people thought it wouldn't matter.
It's a sort of surprising.
Yeah.
So this is rather robust because it is just a gravitational effect of having.
Yeah, and so we've run since then.
Having collapsed.
Yeah, so since then we've run a suite of things that are actually designed to be exactly the Milky Way. So we've pegged the potential to match exactly the Milky Way disk. And we've run that. We've run about 10 of those. And the effect is very robust. All 10 of them, you see it. And yeah, so I think it's real.
How well do you understand the relationship between, so for Milky Way, the relationship between the gas of the Milky Way and the dark matter? So like the gas of the disk, like say the H1.
Yeah.
What is the dark matter distribution in the disk of the galaxy?
Oh, okay. So the question is, what is the dark matter distribution in the disk of the galaxy for, okay. In this simulation, we do not see any evidence in the dark matter for a dark matter disk. That is, we don't see evidence that the dark matter has contracted along the plane of the disk or is co-rotating with the stars in the disk. In the Eris simulation, which I don't have the plot here for that, but in the Eris simulation, I'll just show you the picture, just because I can. They actually find some co-rotation between a subcomponent of the dark matter and the disk, so that there is a small amount of dark matter that's actually co-rotating with the disk. You tend to see this when you have mergers being important. So you tend to see, you create these so-called dark disks when you have a late-time merger with a galaxy that's kind of in plane, and that brings in dark matter and gas, and you can create a kind of like little extra component of dark matter that then moves with, that creates then potentially a weird WIMP wind that you would then fly into or away from, depending on the way it's going around the galaxy. But we don't see that in the fire simulations.
I think we should thank for the time being our fantastic lecturer.
Thank you.